St. Louis University, and we have some participants also from the Office of the President in Malacanang Palace, the DWIZ. Thank you very much. We're very grateful for your presence here in this conference, and we look forward to meaningful encounters and exchanges with you as we share stories and create friendships even after this conference. Thank you very much. And now, to introduce our keynote lecturer for this morning, I have the pleasure on calling on stage Dr. Felicidad Cristina Peñafiel from the College of Science.
Thank you, Mr. Tadeo, for that kind introduction. So, as we are about to embark on a unique intellectual journey that explores intriguing connections between thermodynamics and religion, our next keynote lecturer is a distinguished professor from the University of Santo Tomas, academician, Professor Emeritus Fortunato Sevilla III, Ph.D. So he is a Professor Emeritus of Chemistry at the University of Santo Tomas in Manila, Philippines, and is a member of the National Academy of Science and Technology, and a Fellow of the International Union of Pure and Applied Chemistry and the Federation of the Asian Chemical Societies. He obtained his PhD degree from the University of Manchester in the United Kingdom, where he specialized on instrumentation and analytical science. His research interests include chemical sensors, low-cost chemical instrumentation, and microscale chemistry. He is a faculty member of the College of Science and the Graduate School of the University of Santo Tomas, where he teaches chemical thermodynamics as a part of a course on physical chemistry. So together with this, he brings his wealth of knowledge and insight into this fascinating interdisciplinary field. Please join me in welcoming Professor Academician Fortunato Sevilla III with a warm round of applause.
Thank you very much, Chris, and good morning to everybody. Well, I'd like to thank the organizers for giving me this opportunity to be part of this conference and to be able to interact with a group of different, well, if I can say thinking or culture, from ours. Well, I am a scientist, I teach science, and it is very seldom that we go into a discussion with philosophers, and well, this will be one opportunity to do that. Well, my topic is thermodynamics and religion. Why did I choose this topic? Because I'm teaching thermodynamics in my BS Chem course, and therefore be prepared, for a lecture on thermodynamics this morning. And we'll see how thermodynamics will interact with religion based on your reactions rather than on my inputs. Science and religion, most of the time, they are thought to be conflicting, and therefore we hear about debates on science and religion. However, some will look at it, at the relationship as being complementary, and therefore there are dialogues like what we have in this conference. Actually, there are dialogues being held in different parts of the world. Well, what I've noticed, what I'm aware of is that of the American Advancement Association for the Advancement of Science, wherein they have a, long-running, dialogue on science and religion, Well, I was surprised that in the UK there is no such thing, but there are some institutes, like the Faraday Institute in Cambridge, wherein they do studies on science and religion. For our case here, I'm glad that we have this conference to talk about the relationship of science and religion. Well, locally, I'm not sure whether there have been any other conferences which tackles on this relationship between science and religion. And I'm hoping that This dialogue will be repeated several times, if possible, every year, and to involve not only scientists and philosophers, but also the public in general. Because the perception of the public about science and religion they are conflicting. And it is, seldom that they see that science and religion complement each other. They look at the same end, you know? And, well, science is a very broad field. And for myself, I have focused on chemistry, and for this morning, I will be focusing on one part of, chemistry, what I've been teaching for several years, which is thermodynamics. Thermodynamics is a field of study in chemistry, also in physics and in engineering. Well, from the name, we can guess thermo, heat, and dynamics, which will be about power or changes. And indeed, thermodynamics is about the study of heat and its relation to other forms of energy, while others will say that thermodynamics is energetics. It's the study of energy. Now, what is energy? We have to try to recall your grade school science or your high school science, that energy, I'm sure most of you will have memorized this, that energy is the capacity to do work. But the problem with energy is we cannot see it, but we can feel its effect. For instance, the energy heat. We know that there is this energy which is heat because we see it, and we can measure it through the change in temperature. We know that there is energy which is work because there is some movement, there is some displacement. And it is this, a manifestation that energy is measured and energy is conceived. Otherwise, when we say energy, it seems to be something abstract, but actually it is concrete, it exists, and it is part of the universe. And while we are aware that energy is a current, of current concern, a current issue, because of the shortage, where we get our energy, we think in terms of what moves our transportation and industry in terms of fuel, and also the one that gives us electricity. But we can think also of energy in terms of the food that we eat. It is the one that provides us energy. So the issue about energy is not only about fuel, it's also about food. And the effect of this energy usage is a topic of big concern now. Its effect on climate, and its effect on the availability of power. So that this is the focus of thermodynamics. Thermodynamics, the way I'll be discussing it, is a macroscopic science. It is based on macroscopic systems wherein we can measure macroscopic properties. However, within this macroscopic system, it is thought that there are microscopic particles through whose properties we can explain the macroscopic manifestations of energy in thermodynamics. Well, it has also to be pointed out that thermodynamics is a universal science, that it covers the behavior of the whole universe, both living and non-living, both here on Earth and in outer space. Well, we have to be aware that thermodynamics embodies the laws that describes the behavior of nature, including the events and phenomenon occurring in the universe. Well, in the study of thermodynamics, the focus is usually on a system. A system is a small part of the universe wherein we focus our study, our attention. And how about the rest of the universe? We call it the surrounding. So thermodynamics actually will be about the study of a system, but then the generalization, it is about the universe because, well, the interaction of the system and the surrounding is real and it occurs all the time. Well, the ideas of thermodynamics, the laws of thermodynamics have found application not only in physics, chemistry, or engineering. Well, I was surprised that there are applications in economics. So there is economic thermodynamics, there is social thermodynamics, there is ecological thermodynamics, And in this case, it's not simply about energy, but rather the applications of the laws of thermodynamics to different fields. And this morning, we'll be seeing the interactions of thermodynamics, or the intersection of thermodynamics with philosophy and theology. Well, and it is also seen as a bridge between natural science and the social sciences, because the thinking about beyond the things that is observable, will be coming from the social sciences. And if we look at the history of thermodynamics, it was developed with influences from philosophy and religion, as we shall see from the quotation from the fathers of thermodynamics. Thermodynamics is based on 4 laws. And these laws, well, there are 4 laws, and when I ask the students what are these laws, they will say the first, the second, the third, and the fourth. But no, the last law is the 3rd law, and the first law is not the first law, but the 0th law. How it came to be that way, well, we see in the course of our discussion. But again, let us go back to basic science, and we clarified what is a law. A law is a description of the general behavior of system. It is a summary of what has been observed, and these observations have been confirmed, verified, and re-verified until it has been shown to be consistent. The law is, actually an inferred pattern or regularity in natural occurrences. So it's simply a description, but then it is being interpreted as a rule that nature follows, a rule that governs nature. But we have to go back that the basis is observation. And it has to be differentiated from theory. Well, usually in grade school, high school, and even in universities level science, laws and theories are being interchanged. Well, the distinction being the law describes what happens, and the theory explains the law. Theory is a product of thinking. It is a mental picture, a mental model, which would like to explain the law. And usually, a theory is based on concepts that are unseen, that are abstract. So we hear about atomic theory. It presupposes that there is an atom, but nobody has seen an atom. We see only the effect. Well, to appreciate thermodynamics, let's look at its origin. Well, nowadays, what is being described about the beginnings of thermodynamics is commonplace. But at the start, try to picture the 16th and the 17th century, the people were amazed. And nowadays, we see it as everyday occurrence. When we have a hot body, place it near a cold body, what happens? The hot body will become cold, the cold body will become hot, and in the end, they will have the same temperature. Well, the hot body becoming cold, and the cold body becoming hot. Well, the scientists at the before thought that there must be something that transferred. There must be a substance that transferred from one to the other. What is the nature of this substance? Well, part of the investigations that they had was there should be effect on weight. The system must have changed weight when there is a transfer, but they were disappointed. And there were several studies ending up with that what is involved here is a transfer of energy which is different from matter. And so we hear about the conservation of caloric, and this energy that was transferred, well, we now know as heat, the science that has developed from these observations. And this heat can be used to do work. And this development is the one that led to the design of a steam engine, of steam trains or boats or in industry. So the conversion of heat to work has been applied, and it has contributed much to the progress. It's interesting to see how these conclusion or these properties were arrived at. And the other way around, wherein work is converted to heat. Well, one surprising experiment, and the students could not believe this, that the original experiment was there was system of water which is being stirred. And it was observed that stirring this water caused a change in temperature. Well, you might say, that doesn't happen, What happens is that when we stir coffee, the coffee becomes cold. But when we stir cold coffee, it doesn't become hot. Well, the experiment, we have to be aware that when doing the experiment, there are conditions. The observation that work is converted to heat, that, this was done by Joule, when he stirred the liquid or water, it was done in a condition wherein heat cannot transfer, heat cannot enter or leave the system under insulated or adiabatic conditions. But again, it ended up with this realization that work can be converted to heat, that heat and work are related, and this led to the field of study known as thermodynamics. Now let's discuss the laws of thermodynamics. Be prepared for a lecture, which might be new to most of you, but I'll point out that these are seen in everyday occurrences. The first law, I'm sure many of you will remember grade school or high school science about the law of conservation of energy. Everybody will say, energy cannot be created or cannot be destroyed. And that's actually a statement, that was made by Mayer in 1841. Now, at a higher level, we state the first law as that the energy of the universe is constant. So it now has expanded to include the whole universe. This is the conservation of energy, the first law of thermodynamics, that the energy of the universe is constant. As I've said, thermodynamics focuses on a system, one part of the universe. And this system, this part of the universe is characterized through its temperature, through its volume, to its pressure, and the behavior of the system is based on the microscopic particles, as I've said at the start. And because of these microscopic particles, the system has energy. So a system will have energy, and this is known as internal energy. If we have a glass of water, the water inside the glass has energy. If we have a plate of rice, that rice has energy. And you will not believe it. How come the rice is there and it's not moving? But then what is the evidence that this rice has energy? Eat it. And you will see that it is the one that gives you energy. And also there is conversion. So most of the system, or all of the system, will have energy, and it is known as internal energy, and this energy can be seen as originating from the microscopic particles. But for thermodynamics, we do not pay attention to the microscopic particles. We look at the macroscopic property known as energy, internal energy. And the internal energy of the system can be modified. When we change the temperature, heat will flow into the system. So the internal energy will increase. Or if we do work, or if the system does work. If it does work, the work is being done at the expense of its internal energy. So there is a change. So the internal energy of the system can change because of heat, because of work that goes into the system. With this concept, it's easy to see, to do some mathematics, that the internal energy will change, or that change in internal energy will be due to heat and work. Simple math, and from a simple model. And in the course of mathematical treatment of the equation, and that is characteristic of thermodynamics, it will involve math, plenty of mathematics, not only algebra, but up to the level of calculus and differential calculus. Don't worry, I'll not be going into that. Instead, what we have to note, that in thermodynamics, there are quantities or a group of quantities which keep on recurring. For instance, U plus PV. It will always come out in the mathematics. So what was done? Instead of having U plus PV, they thought, let's give only one letter, a symbol for that, H. And it was given the name of enthalpy. So enthalpy, we have to remember, is a described quantity. It does not exist. It came out as part of the mathematical treatment. But as you can see, and it can be shown, that it has some use. It can be, equated to a quantity that can be measured. For instance, enthalpy can be seen as heat. It can be shown through mathematics that it is equal to the heat that enters or leaves the system at a condition of constant pressure. And in the same manner for internal energy, it is heat at constant volume. And between these two, most of the time, what is expressed and what is encountered is enthalpy, because we have the constant pressure of the surrounding, as being the condition, when we have the usual processes. Well, going back, let's be aware that the internal system belongs to the system. Internal energy is a property of the system. That heat and work came from the surrounding. And this interaction of the heat and the surrounding comprises the universe. And the universe includes everything, within the room, outside Earth, and everything, And that is how, thermodynamics, the laws of thermodynamics stated, and it has been shown, and time and again, shown that it is always true, that energy is conserved, that the energy of the universe is constant. And we have evidences for this. What is lost by the system goes into the surrounding. When wood is burned, we feel the heat that is being liberated into the surrounding. So the heat came from the burning wood. The burning wood loses energy, and it is liberated or released as heat, and we can feel that. And this heat that we can sense or that we can measure will tell us how much is the change in the internal energy of the system. Likewise, if we do work on a system, here we have a gas in a cylinder, or try to picture a syringe, with the end, sealed. Try to push the, plunger in the syringe, you can push it. You are doing work. And doing that, we are introducing energy into the air or the gas that is trapped in the system, or in the syringe, or in this case, the cylinder. How do you know that the trapped and compressed air or gas has energy? Remove your hands, and what will happen? The gas will expand. The syringe plunger will go up, meaning the gas is doing work. And it is doing work because it has energy, the energy that you introduce when you compress the gas. In other words, there is this transfer of energy from the surrounding into the system. And this energy has some use. Here we have the picture, which everybody is familiar, but there is one feature that you should notice, that the cover or the lid of the kettle is rising. And when it rises, it means that it's doing work, that the steam has energy, and that energy is converted into work. The steam can be now to do useful work, and it is being done by, in moving trains, in moving engines. So the trains move because of the energy of the steam. And we also have this, which is, taking place every day, and from which we benefit, that the steam produced by heating water will turn a turbine and give us electricity. And this is the way electricity is being produced. For the power plants, which consumes fuel. The fuel is burned, water is converted into steam, and the steam has energy, and this energy turns the turbine, which gives us electricity. So here we see the conversion from heat to work into useful energy. Within the biological system, within our body, we have manifestations of these. Food is our source of energy. The food that we eat, we metabolize it, and the result of this metabolism will be small molecules and energy, the energy that we use to move around. But together with that, we have to be aware that when eating some food, we feel that heat is being liberated also. And everybody's aware that when we, for those who are, on a diet, they will see the equivalent, the heat equivalent or energy equivalent for some food. That means that if you consume this food, you have to do work equivalent to that. If you do less work, what will happen? Well, the food that you eat or the products will be stored in your body and it will be manifested by a gain in weight or an increase in size due to fat stored in your body. So the first law of thermodynamics shows that energy is converted from one form to the other. The food that we eat is the one that gives us energy. It is the one that is stored also as fat. Another instance is if we leave a glass of water standing, what happens to it after some time? The water will disappear. How do we explain that? The water has evaporated. Some will say, can water evaporate even without heating? We picture evaporation of water as a result of heating. But we cannot deny that water evaporates, even at room temperature. Your wet shirt becomes dry because water evaporates. Why will it evaporate? Well, from where did it get the heat? It came from the surrounding. And what happens to the surrounding when heat was removed from it? The surrounding, you feel that there is a lowering of temperature. You will feel that it's cool. And this is what happens, when you use a fan to make you feel cold, what happened? You feel, cold and comfortable, because of the evaporation of your sweat, Heat will be removed from the surrounding, and it is this removal of heat that will cause a lowering of temperature and an increase in comfort. Our room now has a nice temperature because of the air conditioner. The air conditioner removes heat from this room. How? Through a fluid that flows through it, through freon. Ba't wala? Sorry, hindi ko napansin. Anong nangyari? Kailan nawala? Hindi, kailan nawala yung slide? Ito yung Wi-Fi? Yung may trend? Ito yun. Ayan. Ayun. Okay. So evaporation will require heat, and even at room condition, there is evaporation. The heat comes from the surrounding. So when we perspire and we try to dry the perspiration by using a fan, we feel cool, we feel comfortable because heat is being removed from our surrounding, which is immediately, near your skin. And the same thing for the air conditioner. Well, there is heat being removed by the air conditioner. And, this is through a gas known as freon. Now, where did the heat go? Where did the heat that has been removed from the room go? Go at the back of the air conditioner, and you will feel that the heat that was removed from inside the room is there, being released to the surrounding. So there is a transfer of heat through the freon that is being, that is circulated. However, we have to note here, that for the air conditioner, this is not a spontaneous process. The air conditioner operates because of electricity. Some energy is being produced. But for, the natural process of a liquid evaporating, we see that heat is being removed. So if we have water here around us and let it evaporate, we'll see that there is a cooling effect. And this is what happened under a tree, where there is transpiration. So in the shade of a tree, we feel comfortable that the temperature becomes lower because of the heat being removed to evaporate water from the leaves. The second law. After the first law came the second law, and the second law came out of a realization that the first law is not enough. True energy can be conserved, energy, can be converted from one form to the other, but this transformation, not all of this transformation occur. Example, we have a cup of coffee, leave it, what happens to it? Spontaneously, without doing anything, the coffee will become cold. And nobody had the experience of leaving a cup of coffee cold. And you wanted your coffee to be hot, just leave it there and suddenly it becomes hot. Nobody has seen that because it is not possible, because it is not a natural change, and it is not spontaneous. You want hot coffee? Then heat it. Place it in a heater. But the cold will not become hot spontaneously on its own. And that is what the second law is about. That changes in nature occur in only one direction. The experience of a balloon inflated. Release, the balloon becomes deflated. Nobody has the experience of a deflated balloon. Leave it there and suddenly it becomes inflated. That is not spontaneous. Or water. Water will flow spontaneously from a higher place to a lower place. So we have waterfalls. And there is no tourist spot which has a water rise, wherein water from the ground goes up. Somebody can do that only if you have a pump. But that is not spontaneous. There is already intervention. So the second law tells us that all the changes in nature occur in only one direction. And this change is irreversible. And there are several ways of stating the second law, depending on the point of view. For Clausius, he stated it in terms of the direction of heat flow. And we know that heat will flow from a hot object, from a high temperature to a low temperature. That is the spontaneous, the natural direction of heat flow. Another version of the second law, another statement was made by Kelvin in terms of the conversion of heat into work. And he says that not all of the heat introduced into the system can be converted into work. Introduce 100 joules of heat, you will not get 100 joules of work, which is what is stated by the first law of thermodynamics. The complete conversion of heat into another form of energy, which is work. Instead, what happens? The output is less than the input. And a thought experiment, just to show that this is what really happened, and it's logical. We imagine a heat engine, and it is this model through which the second law of thermodynamics was formulated. Heat can be converted into work. Imagine a cylinder with a gas. We heat the cylinder. We know that the gas will expand. And when the gas expands, it will be doing work, and this is what happened in the automobile. The expansion of the gas formed by the burning of the fuel will cause the piston to go up. But then, that is not the way it is, because what we see in how the automobile works, we have a piston going up and down, up and down. Indeed, the piston has to go down again so that later on it can expand. And so that the gas can expand. But how is this done? By removing heat. Removing heat from the gas, it now goes back to the original, so it can expand, and we have this cycle which results in the continuous performance of work. Note, not all of the heat that is inputted into the system can be converted into work. Some of the heat will have to be released. Some of the heat is wasted or becomes less useful. And in the mathematical treatment of the second law, actually based on that model of the heat engine, again, two quantities came out. Two quantities which were introduced as shortcuts for a formula. Entropy, which I think will be familiar to the philosophers, because I've seen several essays or articles on entropy and philosophy. And entropy, symbol is S, is defined as Q over T. Q is heat, but entropy is not heat. There is over T, temperature. Entropy is not temperature. What is entropy? It is a defined quantity. So it doesn't exist. It is a result of this formula, Q over T. It came out in the derivation, done with the second law. Another quantity that comes out is free energy. And this is a shortcut for H minus Ts. Why H minus Ts? Because it comes out. Instead of writing 3 letters all the time, let's write only one, G. And it was noticed in the course of the derivation that for all spontaneous processes, entropy increases. But, there is one detail that has to be emphasized, that the entropy of the universe increases, the change is towards an increase. And on the other hand, the Gibbs energy decreases. But again, pay attention, it is the Gibbs energy of the system. So spontaneous changes can be predicted, or can be seen to involve an increase in the entropy of the universe, or a decrease in the free energy of the system. And this is the way, this is the direction, in the way all natural changes take place. The hot coffee becomes cold. Time goes forward. Your watch will turn clockwise on it. Time will go forward and it will never come back, or what we say in Filipino, hindi na pwede ibalik ang kahapon, And for the burning of paper, after burning the paper, there is no more paper. You cannot put up together all the ashes and come up with the paper. Well, these spontaneous changes take place irreversibly, only in one direction. And the second law was formulated in terms of this, using entropy, that the changes in nature proceed towards an increase in entropy, or the other way around, that the entropy of the universe tends towards a maximum. Note that entropy is a defined quantity and it cannot be measured. But then there was a mental model for entropy. It was equated with disorder. It was noted that all spontaneous changes in the universe proceed towards a state of disorder, and therefore a model for entropy, which is actually a mathematical formulation, is disorder, that the entropy of the universe increases, meaning that the entropy, that the disorder in the universe increases, and that is the direction of natural changes. And, that is a topic of much discussion, Using visualization in terms of a graph, the entropy of the universe increases, so we know from our math that there will be an upward trend, but then at the maximum, its maximum because it's the highest point, and it's expected to go down. But for entropy, it does not go down. Rather, when we reach the maximum, it stays there. There is equilibrium. There is, well, phase in changes wherein the change will not occur no longer. And for free energy, it is the opposite. Free energy goes towards a minimum. At the minimum, it cannot go up. Rather, it will become constant there. So, a state of equilibrium and a state of equilibrium is a stable state. Going back to entropy. Entropy increases to a maximum, and at the maximum, it remains constant. Remains constant because it's a stable state. And what is that stable state? It is a state of disorder. What does that mean? That a state of disorder is stable. That's a topic of discussion. Now, entropy, as I've said, is equated with disorder. Some will look at it also in terms of the energy that is wasted. Not all of the energy of the system can be converted into work because some of this energy will be liberated as heat at a lower temperature, and as heat, which is less useful. On the other hand, and this is the way chemists and chemical engineers and sometimes physicists we look at the second law, not in terms of what is wasted, but in terms of what can be useful. And it is in terms of the Gibbs free energy of the system. That the Gibbs free energy of the system decreases. Why? Because this is converted into work. And what are the manifestation or evidences of this work? Take a look at the battery. How can the battery give us electricity? This electricity is a result of the decrease in the free energy of the chemical system occurring inside the battery. Imagine a drop of water. We see it as globular, and sometimes we play around with it. We try to stretch the globule, the droplet, and what happens? On its own, the droplet will go back to its original state because there is energy at the surface resisting changes. So these are manifestation of the free energy becoming useful. And this is the way, chemists apply the second law. And it happens through this behavior. Non-spontaneous changes can take place. And this is what is happening. This is what chemists do. This is what chemical engineers and engineers in general do. Making non-spontaneous changes take place. And how? By looking at the changes in the free energy. Consider iron. Leave iron on its own in one corner, what do we see? It becomes rusty. There is rust. Rust formation is spontaneous. Why? Because rust is more stable than free iron. Rust has a lower energy than free iron. But then, from rust, or actually as ores, we can get, again, iron. How? By increasing the temperature or by adding another component like carbon so that rust or actually ores, the one that is used, ores can be converted into iron. And this is how we get iron. The iron that we have is produced in this way. It comes from iron ores, heated and made to react with other substances. So the Gibbs free energy makes non-spontaneous changes possible. Sugar, for instance. We have sugar, leave it there, it remains as sugar. It does not become carbon dioxide and oxygen. But this change is useful, and we can make it take place by mixing it with one substance and by mixing it with a chemical, a potassium chlorate. And this I demonstrate in my lab. I usually demonstrate this in my lectures before they installed the fire alarm systems in the main building. Because, doing this, what happens to the sugar? The sugar bursts into flame, and the room is suddenly covered with smoke, ano? And the table where this was done, well, became dented because some of the wood, ano, was burnt, ano, showing how much energy is produced from sugar. And this is what happens inside the body. We take sugar, sugar is converted into carbon dioxide and water, not directly, not in one explosive step, but the design of, well, chemistry inside a biological system is that these changes take place slowly in the presence of enzymes, in the presence of high-energy compounds like ATP, adenosine triphosphate. So the design of the biological system is that this release of energy will be taking place step by step, slowly, and this is the way we move. When we use energy, so the food that we eat is converted into smaller molecules, and we take advantage of the energy that is released. The third law exists simply to be able to calculate absolute entropy, S. And this dictates that, this will happen at a low temperature. And there is a silhouette law, which was formerly the fourth law, and it has been applied for temperature measurement. And, well, the silhouette law is the principle behind the measurement of temperature. So we see that thermodynamics addresses the questions, will a change take place? And to what extent will it take place? We can make a change take place through manipulation of the parameters. Well, it's almost 5 minutes lang daw, tapos ko lang ng thermodynamics. So I'll go fast with this. Religion, thermodynamics and religion. The first law. Whenever the first law is stated that that energy can either be created or destroyed, some student will ask, why do we have energy? If it cannot be created, why do we have energy? Well, making them think, they will come to the conclusion that there was energy that was created at the start, and that this energy is part of creation. It's impossible for energy to exist or come out of nowhere. It has been created, and it is part of the creation. We have the story from the Genesis, that on the first day, what was created was light. Light is energy. And from the energy of the light, some other changes, the other changes, and the energy that occurs in the universe until now is part of this energy that was created on the first day of creation. So thermodynamics, leads to the realization of the existence of a creator. But how come the energy of the universe remains constant? Because creation was done within the 6 days, and after that there was no creation, so the amount of energy has remained constant since the time of creation. So we see that the first law is about a balance of energy loss and energy gain, as I've said. Well, this can be applied in several ways. So we have this saying, 1 man's loss is 1 man's gain. And we have several biological systems, wherein the system has to die in order to give life, so that life can continue. And extending also to what we have in religion, that there was this supreme sacrifice of the death of Christ, to redeem man. Well, the second law emphasizes that some of the energy will be degraded to a lower form of heat, that is unable to produce work. And this happens in the universe. And this implies that there is a beginning and that there is an end. And again, there are many discourses that can be, done on this. And there is also this idea of a heat death of the universe, because at the end, that the energy, the useful energy of the universe will be consumed, and after that, we have the end of the world universe, and this is known as heat death. And I've read several discussions on this. And, well, we can picture this change that energy is increasing and become constant. So this is the state of maximum disorder, or the free energy of the system becoming lower. And here we have the state of less amount of useful energy. And indeed, the second law has provoked much discussion and debates among scientists, theologians, and philosophers. So here, there are beliefs that science and religion should be independent. On the other hand, there are conclusions that science and religion fortify each other. So there is this theory of evolution, which says that organisms became better over time. That this can be interpreted that there was order. That order came out rather than disorder. And this is contrary to the second law. But then we have to remember that the second law says it is about the disorder of the whole universe. And for entropy, it only considers the increase in order of the species, of species on man. So it is not in conflict with the second law. But then, still, this evolution theory assumes that there is an initial state, and this initial state came out of creation. So there is no conflict with the concept of creation. The Big Bang Theory. The Big Bang Theory says that at the start, the universe was a small sphere wherein there is low entropy, and it expanded to form a high entropy universe. Again, this is in consonance with the second law. But again, for creation, where did this initial sphere come? Well, it has to be created. So we see that the laws of thermodynamics is a manifestation of the logic and the intelligence that was built in the universe by the Creator. And for thermodynamics and for science in general, it is a fulfillment of the task of man to explore as the peculiarity of the universe. Genesis was stated, fill the earth and subdue it. Subdue it not in terms of using it for your convenience or benefit, but rather to explore and reveal the logic, the intelligence, the beauty, and the order that we have in creation, in the universe. And this is the essence of, well, the way I look at science, Science to reveal the order of the universe, to reveal the design, And in studying chemistry, we see this order, the order, through the chemicals, through the structure of the molecules, that naturally these reactions will take place because one molecule has a positive side, the other molecule has a negative side, and it is inevitable that these two will interact and lead to many reactions. And for thermodynamics, well, this is also the view that the founders of thermodynamics had, to cite from James Joule, who was one of the scientists who formulated experiments, that I shall not lose no time in repeating and extend this experiment, being satisfied that the grand agents of nature are by the creators, fiat, indestructible, and etc. And in another quotation, it says that it is evident that an acquaintance with the natural laws means no less an acquaintance with the mind of God therein expressed. Planck, another pioneer in thermodynamics, says that science and religion, in their ultimate effect, are headed for the same goal, the recognition of an omnipresent intellect ruling the universe. Kelvin, and everybody's familiar with the name in terms of Kelvin temperature, Well, he has several quotations that shows his belief in a creator. I cannot admit that with regards to the origin of life, that science either affirms nor denies creative power. Science positively affirms creative power. And in another speech, he says that do not be afraid to be free thinkers. If you think strongly enough, you will be forced by science to the belief of God, which is the foundation of all religion. we will find science not antagonistic, but helpful in religion. And indeed, we can see science and religion going towards a direction, and this is, well, the result of the dialogues in revealing the same goal, the same conclusion that we have in science and religion. Thank you.
So thank you very much, Academician Professor Fortunato Sevilla III, for helping us appreciate and thermodynamics through your simplified examples, which can help us further understand the different laws of thermodynamics and to be able to complement thermodynamics and religion. So I'm sure a lot of people in the audience, together with myself, when we saw the topic thermodynamics, it brought a little fear in our hearts. So through his very interactive lecture, I'm sure you have a little bit more background in thermodynamics. So right now we're going to open the floor for questions from the audience. So since this is a hybrid conference, we'll entertain questions from both on-site and online participants. So for our on-site participants, so please allow me to call you. So raise your hand and approach the mic in front. Introduce yourself and you may pose your question.
Good morning, sir. Alvin from De La Salle University, graduate student of philosophy. Now, Kalam cosmological argument tells us that everything that began to exist has a cause. The universe began to exist, therefore the universe has a cause. Now, the second premise of that argument is heavily proven by the second law of thermodynamics. And all the cosmic background radiation, the development, the discovery of Hubble, the redshift and everything. Now my question is, what do you think is the strongest opponent or challenge to the second law of thermodynamics as a premise to that second premise in the argument, in that Kalam cosmological argument for the existence of God? For the existence of God.
Well, as I have, as I've declared at the start, I am a scientist, and I know only science.
Yeah, but
now we have to just adjust our thinking, and being able to answer that well. For this talk, I have extended my thinking, to go into the wavelength of philosophy and theology.
Yes.
Now, for the second law of thermodynamics, you said that how can it be?
What's the strongest challenge or opponent of the second law of thermodynamics?
Well, the goal is to be able to explain everything what happens in the universe. Well, it's easy to explain what is spontaneous, what has been seen. Now, it is through thermodynamics, it is through the second law that non-spontaneous changes that do not take place in nature, can be made to take place. It is through the application of the equations, this mathematical, of thermodynamics, that we can make non-spontaneous changes take place. And this is the application of chemistry, physics, and engineering. We can say, making the impossible possible. Not in terms of creating, but in terms of coming out with products or effects that will be beneficial to man. So for me, that is a challenge in how to make changes take place for the benefit of man, to improve life, etc. Okay?
Thank you, Professor Sevilla.
So, thank you.
Havermark. Thanks for the lecture, wonderful explication of the basic ideas in thermodynamics. My questions, they go to the link between science and religion, as it is the main problem discussed. First of all, let me go back to Joule, as you finished with him. Of course, the brilliant example of discoverer, a great figure in the history of science. I found one quotation with Joule, and this shows a possible danger to link science and religion too strongly. Of course, I do not want to complain Joule because he was a child of his times and so on. But anyway, let me quote quickly. This is the old language. It is that order is maintained in the universe. Nothing is deranged, nothing ever lost. But the entire machinery, complicated as it is, works smoothly and harmoniously. And as in the awful vision of Ezekiel, will may be in the middle of will, and everything may appear complicated and involved in the apparent confusion and intricacy of an almost endless variety of causes, effects, conversions, and arrangements, yet is the most perfect regularity preserved, the whole being governed by the sovereign will of God. And this is the philosophical and theological problem of the order in the world, found by Joule as the way to express his faith. It is up to you a bit of danger to link science and religion in that way?
Well, the way I see it, that all the changes, the changes in the universe is complicated because, one effect will lead to another effect, etc., etc. Well, in the course of thermodynamics, a technique, in the mathematical treatment of thermodynamics, is to divide the problem into small bits. And in these small bits, we can solve for some of the functions and show that this will take place. And also by combining these small bits, we can see why a change will take place, why this happens. So the view is rather than looking at the whole, we look at the different parts and appreciate each part. And and we see also that within these small parts there is order. Did I answer your question?
Okay, thank you. It's easy to depict that maybe Joule's view was too optimistic to find an order in the nature in the deepest possible way, as it is written directly by him. But thanks a lot. And the second question is quite short, directly connected to your speech. That is to say, loss of nature problem. And as you mentioned, it can be regarded as a description of what happens in the world, description.
Yeah.
But there is also another way to think about the loss of nature as prescriptive. Not only as something that describes what happens, but also what makes nature working, a kind of force behind everything. It's much more than only a description. What's the way to combine these two views? Thank you.
Excuse me. I'd like to ask you a question. Well, regarding the last statement that you said, for us in science, we see this law as a description of what happens, and that's the origin. But from your point of view as philosophers, you see it as a prescription that the universe should follow this. Is that correct?
So I
Well-
am of the opinion that it is not only a description, it is something more than description. Laws of nature, in the Platonic way of interpretation, they are behind everything that happens in the world. Not only what is possible to be described by the language of math, of course, as it is in sciences, but also a kind of, for example, regularities and relationships in nature. This is the genuine portion of the laws of nature.
Yeah, and I think also we can say that that is what science is all about. Trying to discover the laws of nature. Based on this observation, deduce that because of the regularity that is taking place, that has been observed, that this must be the law of nature. Is that a correct?
I am not an expert of everything, but let's make our discussion longer in the break. Thank you so much.
Thank you very much. So at the back.
Hi, good morning, Professor Sevilla, Jesse from the Department of Philosophy here in UST. I find the lecture interesting in many points coming from the perspective of philosophy. Maybe what I could gather from the talk is the dynamics of movement and transition of things from one point or form into another through energy transformation. Parang ganun po. It is as if thermodynamics is suggesting that transformation, change is inevitable. And from the tiniest, examples a while ago, the tiniest minerals or material components of minerals, they can transform into something else. Perhaps ingredients for infrastructures, heat converts into electricity, light into energy. So everything changes, and I really find it bothering in a positively curious way. Since in philosophy, and perhaps I think in religion too, there's always been an articulated disdain for flux, change, motion in general. In the ways we purge change in the name of something permanent. For Plato, it's the forms are permanent. In Aristotle, the first mover remains unmoved. In Christianity, we want something constant or permanent like eternal life. In politics, we want stability. Even the state itself is, it came from the word stasis, which means rest. Well, yung archaic version of stasis is civil war, pero I like rest as its meaning or etymology. In normal life, we want convenience and rest, which is the absence of movement or the possibility for change or transformation, prompting us to not move and change anymore. Rest is the absence of motion. How might thermodynamics convince philosophy and religion to be more accommodating to change or perhaps transformation? Yun lang po. Thank you.
First, not all changes are possible. That is what the second law says. That we have to differentiate changes that take place spontaneously. What we observe, what takes place in nature are spontaneous changes, and the second law says that the direction is described by an increase in entropy, by an increase in the entropy of the universe, of the whole universe, or by a decrease in the free or available energy of a system. That is a natural change. But then there are changes which will not be according to that, and which we feel that is needed. And it is there that we have to do something, try to force what nature does not allow spontaneously, meaning that there is now human intervention. And therefore, we see changes taking place. In politics, we want a change in the government, so we have to do something. So we can cite several other instances wherein man has to do something in order for change to take place. You want to be successful, you have to exert effort. No gain, ano? Paano yun? No loss, no gain, ano? So that means that you do not become successful spontaneously. You have to exert some effort to do that. So these are changes wherein some intervention has to be done. These are not spontaneous changes. So, anong comment ng mga philosopher? Yeah.
So we have a question at the back po muna. Sorry about that.
I'm Father Anthony from Casisiaco, Recoletos, in Baguio City. Yes, God made the order, but when man was created, then comes the disorder. I'm into the practical side, sir. We're talking about some change and an entropy, for example, because I'm handling also natural cosmology, natural theology, philosophy, I mean. I'm telling my students, especially towards the end, in the application, that whenever we take out anything as a source of energy, then naturally it would end up to heat. As you said, heat end as a possibility of the end of the universe, right? And so, for example, anything, God created everything in order, places everything in order. What is there inside the earth or every planet has a reason why they are placed there. And all those things also, as human beings, placed above the earth and all the atmosphere outside the earth has or have the certain reason why those things are arranged that way. Now, nowadays, because of the need of man, because of technology and so on and so forth, we now draw out a lot from fuel under the earth and so on and so forth. Now from, for example, for the use of our gadgets, they are taken, right? So anything that are taken down out, for example, inside or down the earth, then there is no way for us to replace it, correct? As our own way also of taking place or making the so-called the world in balance or in order. So the consequences would also be drastic, and I don't know, because this is now a challenge for all of us. And you, sir, then as a scientist, the one then talking about this, know also the possibility if we cannot do something nowadays. Yes, there are a lot of advocacies regarding ecology and so on and so forth. But all these things, the use of fuel, the use of material, the use of diamond and gold taken down from under the earth, we are not quite familiar that this has also drastic effects to the totality of energy as a closed system. And so the question is your own challenge for all of us, and then part of our research also to be aware of all these things, and what can philosophers do as a response to all of this. Thank you.
Please, hindi ko na masyado naintindihan. So what's the question?
Because we know all these things, like we take all these things, so what are possible challenges, source of research, points for reflection, points for discussion, for science and philosophers, not only religion, for us to respond to it, not only about theoretically, but realistically as a response to all these things, because not only that we see the theory, but we see the practicality, the use of all these things now, that our research will become now applicable, realistic, that we are going to respond to this call of the love of earth, of the Mother Earth, because we know of all these things. The application of science, scientific principles, and philosophical principles are also good foundations for us to realize that we need to take a stand, make a move, an action, in order to respond to this greater task of, say, even suspending the increase of entropy, and also suspending the increase of heat, and of course, at least delaying the possibility of increasing the heat in the universe. Thank you.
Well, in terms of entropy, we talk about the universe. Well, the other part of the second law is in terms of the free energy, the energy that is available for, and what happens, is that this is decreasing. And in a way, this is related to the concern about energy shortage. Well, some of the students, my students, were saying, how come we're worried about energy shortage when the first law says that the energy of the universe is constant? There is no shortage. But what has to be clarified is that what is being lost, or what is in short supply is the useful energy, and that is entropy. Now, we talk about entropy of systems. These are part of the universe. And, well, if we try to think in terms of that, well, I think we can have an effect that will be beneficial to a bigger system. So as I have said, the approach that we have in the study of thermodynamics is to break it down to small problems and solve these problems and put them together to come out with the whole. And for solving problems, well, some will say that we tend to look at one small part and not pay attention to the other, the effect that it will have on the other system. Well, we have learned and we are told that we have to consider not only the benefit that we have, but also its impact on the environment. And conversely, we also have to be concerned what we do to the environment also have impact on man. So, well, here there is this challenge in looking at these happenings in two different views and coming up with the same conclusion. Have I answered the question or what? Ayun na.
Okay, sir. It was only actually your own, I say, in scientific field only that what we can do is that we are aware of these things, conscious of these things. It's because awareness of these things also will lead us to further reflections. And how can philosophy also, like in our research also, respond to this possibility? Because it's not only the work of science, but philosophy, I do believe, can help in also responding to this challenge, because this is a reality. That is my point. Now, on your part, how in your science field, in the scientific field, how can we respond to it now? Because you have already presented to us these principles. Principles would lead us, or theories would lead us to the possibility of answering many claims, many theses, many research, and many problems confronting life, our life situations. Thank you.
Okay, so thank you very much for that comment. So we have a very short amount of time left, so we will entertain Dr. Aguas first. So maybe you can continue your discussion with Professor Sevilla during the break.
Okay. Thank you very much, sir. I'm not going to ask question, but I'll just express my appreciation to your presentation. You have provided us with a first-hand experience of how a scientist, thinks. You have provided us with your perspectives, with your thoughts, with your ideas. It's actually a breakthrough to the dialogue that we are having right now, and the kind of dialogue that probably we can continue in the future. So this is a great opportunity for us, for philosophers and theologians, to listen to a scientist, how the mind of a scientist works, his perspectives and his views. And we are truly appreciative of your time and your presentation, sir. So thank you very much.
Pwede mag-respond ng sandali? Well, actually, for me, and we have been trying to do something about this, is to have this conferences or dialogues or discussions, between science and religion. Well, many years back, we had this conference on the ethics of emerging technology. Well, here we have this, philosophy or religion with the high technology that is coming out at the time. And nowadays, yesterday we have this neuroscience discussion, and there are several other discussions, and I think we will not run out of topics. And to have this dialogue conducted regularly, if possible, yearly, this will be, it will be nice. And, we can involve different other scientists, for this conference, you limited your scientists from people here in the university, and I'm sure, the other scientists from other universities and from other institutions will be willing to engage in this discussion. And another thing, that the results of this discussion should be made known to the public. The public has to know that, okay, there is a discussion between science and religion, that because the common perception is that science is against religion, and religion is a hindrance to science. Now, if we can make the results of discussion be made known to the public, or even make the public be involved, then I think we will be achieving a greater end. Thank you.
So right now, we will have to close the floor for any further questions, but you can continue the discussion during the break. So once again, let's thank our esteemed keynote lecturer, Professor Academician Fortunato Sevilla III, for his excellent talk and discussion.
Thank you, Dr. Peñafiel, for moderating our keynote lecture this morning. So, are we still okay? So, of course, minus all those chemical formulas and mathematical equations, I bet our philosophers and our theologians will have something to add to their lectures in the coming semester for their philosophy of religion, science, and those of you who are teaching the existence of God, creation, and all of that. So thank you very much for that brilliant presentation, sir. So at this point, we would like to present our certificate of appreciation to Professor Sevilla, and the certificate reads, the Pontifical and Royal University of Santo Tomas, the Catholic University of the Philippines, through the Center for Theology, Religious Studies, and Ethics, Institute of Religion, the Ecclesiastical Faculties, and the Philippine National Philosophical Research Society, presents the certificate of appreciation to Professor Academician Fortunato B. Sevilla III, Ph.D., for generously sharing his knowledge as a keynote lecturer presenting a paper entitled Thermodynamics and Religion during the John Paul II International Conference with the theme God and the World, Dialogues on Culture, Religion, and Science, held on June 26 to 28, 2024 at the Thomas Aquinas Research Complex, University of Santo Tomas, Manila, Philippines. Signed, Professor Joel C. Sagut, Ph.D., Director, Center for Theology, Religious Studies, and Ethics, Professor Jim S. Aguas, Ph.D., Executive Governor, Philippine National Philosophical Research Society, and Reverend Father Herminio B. de Gojoy, OP, Ph.D., Dean, the Faculty of Philosophy. So just a few reminders before we go on our fourth parallel session. So the parallel session, we have to adjust a little bit of our time. So the parallel session will now begin right now, just 5 minutes, and then we'll run until 12:30. We will have a shortened lunch break because our time is compressed already. So we have to be back here at 1:15 1:15 in order to witness the oath-taking of the new officers of the Philippine National Philosophical Research Society. So I think everyone knows already where the parallel sessions will be held at the third floor, and then we will have our lunch break at 12:30. So please be back here at the auditorium at 1:30, exactly 1:30. 1:15, I mean. So thank you very much, and hope have a great parallel session and lunch break. Thank you.